Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor in the Department of Computer Science at Jesus and Mary College, University of Delhi. So friends, in the series of operating systems, we have been talking about different aspects related to process management, and we are in the last lecture of this series, we were talking about process synchronization. So we shall be continuing with the topic of process synchronization, and a quick recap will place us in the perspective of where the discussion was. So basically in the last we were talking about how shared data can be modified and how what leads to race condition and what is critical section of a process, and how we need to tackle this problem of critical section. So generally there are two approaches which are used to handle critical sections in operating systems. First is the preemptive kernels and the second is the non-preemptive kernel. So preemptive kernel basically allows the processes to be preempted or interrupted while it is running in the kernel mode, whereas if we see a non-preemptive kernel, then it does not allow a process running in the kernel mode to be preempted. That is, a kernel mode process will run until it exits the kernel mode, or it blocks, or it voluntarily yields the control of the CPU. Now non-preemptive processes will not have the race condition, because they will have the sole control of the data structures. So therefore there is no possibility of a race control on kernel data structures when only one process is active in the kernel at a given time. But preemptive kernels, they have to be carefully designed, because they need to ensure that the shared kernel data are free from race conditions. So therefore preemptive kernel may be more responsive, because there is less risk that a kernel process mode process will run for an arbitrarily long period of time before relinquishing the processor or waiting for the other processes. So basically if we are looking at a non-preemptive kernel, it means that once the processor is taken up by the kernel mode process, then it is not going to leave it. So therefore this system is actually not suitable for real time programming, as it will not allow the processes to preempt a currently running system. We need to have a more responsive real time system, where the processors can be asked, or the processes can be asked to relinquish the processor for giving a chance to any other waiting processes. So therefore in this whole idea of how the race condition needs to be prevented and how critical section can be executed, a very classic software based solution is given by the Peterson's solution, or this is a software based algorithm which talks about how critical section can be dealt with, how this problem of critical section can be solved. Now because modern architectures, they perform basic machine language instructions like load and store instruction. So there is no guarantee that Peterson's solution will work on such architectures. However, even though it is not going to be supported by modern architecture, still Peterson's solution is very important, because it provides a very good algorithmic description of solving critical section problem. It illustrates some of the complexities which are involved in designing softwares which address the requirements of mutual exclusion, progress and bounded waiting, because we had seen that any solution which is given for the critical section problem has to address these three requirements, has to meet these three requirements of mutual exclusion, progress and bounded waiting. So Peterson's solution is actually restricted to two processes only, which alternate execution between their critical section and the remainder sections. So this is another drawback if we say that Peterson's solution only talks about two processes in a system, which is not in multiprocessor modern day system, it is not viable, because there is n number of processes. So if we look at the Peterson's solution for the sake of understanding and to understand how an algorithm can be defined which meets the three requirements. So we see that there are two processes which are numbered as P0 and say P1. So for our convenience we will say the processes are Pi and say Pj, right, where one is less than the other by 1. So in Peterson's solution we need two processes which share two data items. So the first data item is known as turn, and that is an integer type of data, and the second data item is a boolean which is called flag. Now this boolean flag is actually an array of size 2. Now why we are creating an array of size 2? Because we have seen that Peterson's solution only gives the solution for two processes. We have said that only two processes are dealt with in this. So we have two processes, Pi and Pj, and turn is of course an integer variable. Now turn variable actually indicates whose turn it is to enter the critical section, that is which process is going to enter the critical section. So if we say that turn is equal to I, it means that the process Pi is going to execute, is allowed to execute in its critical section, and the flag array is used to indicate if a process is ready to enter the critical section or not. So flag I means that the process Pi is ready for entering the critical section. So now this problem, basically the Peterson's algorithm is a very humble algorithm if we see, because in this case the process Pi is going to allow or is going to give the turn to process J, and the process J is going to allow and give the turn to process I. So this type of algorithm is known as a very humble algorithm. So if we look at this algorithm here, it is a simple algorithm where we are saying how process I is going to go into execution. So we say that initially the value of flag I is true, because we said it is boolean, so it can have only two values, that is either true or false. So flag I is true means that the process I is ready to go into its critical section, and the value of turn is given to J, that is the process which is going to access the critical section is J. It is J's turn, the process J's turn to access the processor to get into its critical section execution. Now we have this while loop which is very interesting, where we have two conditions and both the conditions have to be true for the execution. Now what are the true conditions? So we already said that this is an execution for process Pi, and we said that this is a humble algorithm. So because this is process Pi, but it is giving the turn to J. Now in this while loop when we see that there is this flag J and turn is also equal to J. That is, if both these conditions are true, then nothing will be done, because we can see that there is a semicolon after the while loop. So when both the conditions are met, the while loop terminates there. Only when one of the conditions is false, then it will come in its critical section. That is when either flag of J is equal to false or turn of J is not equal to J. That is, only then process Pi will execute. So none of the conditions, both the conditions are true, then the process Pi will not go into its critical section. But if it is one of the conditions become false, then it will execute the critical section. So process Pi will go into its critical section. After the process Pi completes its critical section, then it will set the value of flag of I. That is, now the process Pi is not ready. It is setting it to false. It means that process Pi is not ready now. That is, process Pj can execute now. So and then of course there is the remainder section. So basically this while loop will execute for process Pi. If we look at the loop or the process, how the critical section for Pj is going to execute, it is going to be just the reverse. So this point is very important to have understood this while loop, and this semicolon which is put after the loop is going to make the the difference in the humble algorithm. So to enter the critical section, Pi will first set the I to be true, and then it will set turn to value j, because it is a humble algorithm, and then it will assert that if other process wish to enter the critical section, then it can do so. It will allow process Pj to enter the critical section. Now if both the processes they try to enter at the same time, that is turn is set to both I and j at roughly the same time, because we are saying that there are two processes which can have which can try to enter the execution. So both try to enter, that is I and j both get the value, assign the value to turn, then that is not possible, because only one of these assignments will last, the other assignment will be immediately overwritten, right. So eventual value of turn will determine that which of the two processes allowed to enter the critical section first, whether it is our turn is equal to I, then process Pi will go into the critical section. If turn is equal to j, then process j will enter its critical section, but turn can never have two values. So this is very important, that one value will be overwritten by the other value immediately when both the processes are trying to enter the critical section. So now this algorithm is clear, and it makes sense that this is a humble algorithm and processes can execute without having a race condition their critical section. Now it is very important to also understand that whether this Peterson's problem is meeting the three conditions, whether mutual exclusion is preserved, whether the progress requirement is satisfied, and whether bounded weighting requirement is met. So it is very important that the three conditions should be met for Peterson's solution to be approved by as a valid solution for the critical section problem. Now first is that we have to see whether mutual exclusion is preserved. So mutual exclusion means that if one process is entering into its critical section, then no other process can be allowed to enter the critical section. So to prove this property, that is mutual exclusion, we note that the process Pi will enter its critical section only when the conditions are false, that is when flag of j is false or turn is equal to I. Either of the conditions has to be false, because we have seen that in the while loop. Now we note that if both processes can be set or can be executing in their critical sections at the same time, right, then flag of 0, that is Pi, and flag of 1 both are equal to true, that is both are ready to be executed, both are ready to go into their critical section. So these two observations imply that P0 and P1 or whatever Pi and Pj, they could not have successfully executed their while statements at about the same time. Why? Because since the value of turn can either be 0 or it can be 1. The value of turn cannot be both, because we have just seen that the value of the variable turn will be overwritten, right. So therefore one of the processes, whether it is Pj, must have successfully executed the while statement, whereas Pi had to execute at least one additional statement, that is it has to assign the value j to turn, so that j can be assigned to the processor or j can start its execution. So however, at the same time flag of j is equal to true and turn is equal to j, and this condition will persist as long as Pj is in its critical section, because j is executing, so turn is equal to j. So therefore mutual exclusion will be preserved. So therefore first condition is met by Peterson's solution, that only one process will be executing its critical section at a given time. Now if we look at the two other problems, that is the progress requirement is satisfied, that is no process, if one process is waiting, if there is no process which is in execution, if no process is executing its critical section, then another process can be given the chance, and bounded waiting requirement, that is every process will have a limited waiting period after which it will be getting a chance to go into its critical section. So both these requirements have to be met by Peterson's solution. So we prove these two properties, that is of progress and bounded waiting, and we note that Pi can be prevented from entering the critical section only if it is stuck in the while loop with the condition where we say flag j is equal to true and turn is equal to j. So this loop is the only one possible loop by which we can prevent Pi from entering the critical section, because till the time this loop is true, Pi will not enter the critical section. If Pj is not ready to enter the critical section, then we will say that flag of j will become false and then Pi can enter its critical section. If Pj has set the value of flag j to true, that is now Pj is ready to be executed and is also executing in the while statement, then either turn is equal to I or turn is equal to j. So if turn is equal to I, then Pi will enter the critical section. If turn is equal to j, then Pj will enter the critical section. However, once Pj exits its critical section, it will reset the flag j to false, because now once it is completed executing its critical section, it is no more ready, and therefore it will allow Pi to enter its critical section. So what we are seeing is that the processes, they are taking turns, that is one process cannot hold the execution unlimited, or it cannot hold it for a longer period of time, and they constantly keep switching between each other. So because they are now, Pj is setting the value of flag j to true, which is also, it is also setting the turn to I, because we have seen that the process is always giving a turn to the other process. So process Pj will give the turn to process I. Thus, Pi does not change the value of the variable turn while executing the while statement. So Pi will enter the critical section, that is it will progress at most one entry by Pj. So therefore, this is the problem of bounded waiting, that is the process is going to be, no process is going to have a wait for a long period of time. There is a limit bounded, there is a bound up to which the process will have to wait for execution of its critical section. So friends, this was one aspect of solution to the critical section problem, that is a software based classical solution. Then we also have hardware based solution, and we have hardware based synchronization solutions which are available. So besides this software based technique, we have hardware to software based APIs which are available for both kernel developers also and for application programmers also. So all these solutions, they are based on one premise, that is the premise of locking. Locking means that we are protecting the critical region through the use of locks. Now this could be implemented using hardware or it could be implemented using software. But if we say that it is hardware features, they can make programming task easier and they also improve the system efficiency. So what we look at is, we look at a hardware based solution for synchronization problem. Now the critical section problem, it could be solved simply if you have a single processor environment, right? Because in this case we could prevent interrupts from occurring while a shared variable was being modified because there is only a single processor. So, we can always be sure that the current sequence of instructions will be allowed to execute in order without any preemption, because there is one processor and one processor is assigned this task, and that the process is going to access the shared variable. No other instruction will be running. So, no unexpected modifications could be made to the shared variable. Now, this is often the approach taken by non-preemptive kernels. We had seen in non-preemptive kernel processes also the same thing is happening, where one process cannot be preempted. So, here also, because it is a single processor system, this system is working well, but this is not a feasible solution in case of multi-processor environment, because if you disable the interrupts on a multi-processor environment, then it can be very time consuming, because you have to send the message to all the different processors that the interrupt has been disabled and the process which is running cannot be preempted. So, therefore, this message passing delay is going to decrease the system efficiency, and also it is going to have effects on the system clock, because the system clock is also to be kept updated by the interrupts. So, most modern computer systems, therefore, they have a special hardware instruction, and this hardware instruction allow us either to test and modify the content of a word or to swap the contents of two words atomically. Atomically means that it is going to execute one at a time and it cannot be interrupted. That is, it is an uninterruptible unit. If one function is being executed, it will execute completely. It cannot be preempted in between, it cannot be interrupted in between. So, we can have these special instructions to solve the critical section problem in a very simple manner, right. So, what we are doing is that instead of discussing specific instruction, we are going to talk about the two types or the main concept of instructions here, and these are two instructions that we call, this is the test and set instruction, and we have the compare and swap instruction. So, we are going to talk about the test and set instructions and not about the compare and swap instruction as a part of this lecture. So, if we look at how the test and set instruction it implements mutual exclusion, very interesting. So, we have this while loop where we have a lock which is given. So, again there is a semicolon after the while loop. So, till the time this condition is true, the system is not going to do anything, the process is not going to execute, because the value of lock is true, right. So, if this value becomes false, that is, if the value of lock is disabled, then the process will go into its critical section. Once the process executes its critical section, it will again make the value of lock as false, right. So, and then there is remainder section. So, important characteristic is that this instruction, the lock instruction, the set instruction, the test and set both instruction, they execute atomically, right. That is, if they are executing simultaneously, that is each one on a different CPU, they will be executing sequentially in some arbitrary order. If the machine supports the test and set instructions, then we can implement mutual exclusion by declaring a Boolean variable called lock, which you initialize to false. False means that the process cannot, the process is actually, the critical section is locked. In this context of locks and how hardware based solutions are given, we have another type of lock which we call as the mutex locks. Mutex locks, the word mutex actually comes from mutual exclusion. So, these are mutual exclusion locks. Now, here also the hardware based solution, whatever we have discussed, these are complicated and therefore, these are generally not accessible by many application programmers. So, instead of this, operating system designers, they build their own software tools to solve this problem of critical section. So, the one of the simplest tools, which is again a software based tool which has been designed by operating system designers, is the mutex lock. Mutex locks basically, they protect the critical region and they prevent the race condition. That is, a process must acquire the lock before entering a critical section, and it will release the lock when it exits the critical section. So, there are two functions actually, the acquire function which is going to acquire the lock, and the release function which is going to release the lock. The mutex lock has a boolean variable available, and the value of this variable will indicate whether the lock is available or not. So, if the lock is available, then there is a call to acquire, and that call will be succeeded. If the lock is then considered unavailable, once the lock has been acquired, then it will become unavailable, and if a process is attempting to acquire an unavailable lock, then the process is going to be blocked till the time the lock is released. So, this is the acquire function, that is only when there is the lock is unavailable, only when it is not available, it will go into a busy wait. The process will go into a busy wait, okay, and when it gets the lock, it will make the available variable set to false, because the lock has been acquired by this process. Now, this is another solution to the critical section problem, where the process will first ask for a lock. So, it will run the acquire lock process. After the lock is acquired, it will go into the critical section problem. In the critical section, once the critical section has been executed, it will release the lock and go and execute its remainder section. So, what is the release function? In the release function, it is going to set the value of the boolean variable available to true, because now the lock is available for being assigned or for being acquired by another. Now, calls to either acquire or released, they have to be performed atomically. That is, if you are the acquire process is executing, it has to execute completely. So, mutex locks, they are often implemented using hardware mechanism. Of course, we are not going to discuss the details of how mutex locks are going to be implemented, but the main disadvantage of the implementation is that this requires a busy waiting. Busy waiting means that the process will continuously go on checking whether the lock is available or not. So, if it is a single processor environment, this can lead to a lot of CPU cycles being wasted. In multiprocessor, still one thread can go in busy wait, the other thread can go on continue with the execution, but this busy wait in which a process goes continuously in the loop checking whether the lock is available or not, can lead to a wastage of CPU cycles. So, this is all about the mutex locks that we have discussed. We will be continuing our discussion on process synchronization in the future lectures. Till then, keep watching CEC. Thank you.